All right, guys, so what we're going to be doing here is we're going to be looking at the second part of the review. If you haven't watched the first part yet, if you haven't done the first part yet, they're actually like independent of each other. So if you're working on the second part already, that's totally fine, not a big deal, but know that this is the second part of the review as we jump in to look at these problems. So we've got this problem right here, okay, and for the first 5 questions, we're going to use the following information. A polar bear is riding on a unicycle on a tightrope. The bear's position can be defined by the equation P of t equals, and we have this function right here, this 3ln of 0.2x to the third on the interval from 0 to 10, where t is time in seconds and the position is measured in meters. So basically what we have to understand here is this is an equation that is giving us the position. This polar bear, it's really just like a particle motion problem. This polar bear is just moving back and forth and back and forth, but it's really just on a unicycle, so it's just moving in one dimension. Now, the first problem wants to know what is the velocity of the polar bear at time equals 5.5. Well, to get from position to velocity, what we have to realize is we're just going to take the derivative of our position function. So I leave the 3 there, and then I multiply that by 1 over 0.2 x to the third, because that's how we take the derivative of the ln of something. And then we multiply that by the derivative, squared, by the derivative of what's on the inside of the parentheses. So we're applying the chain rule. So that is our velocity function. Now, if I want to find out what the velocity is at that time, we just take our calculator and we go 0.2, and instead of plugging in x right here, we're going to put 5.5 everywhere that there is an x. So I've got 5.5 x squared, or 5.5 squared right there. And when you type that into your calculator, at least what I got, and this number I'm not 100% positive is right, but the process is correct, 1.636, and don't worry about the units, it would be meters per second, but that would be the velocity of the polar bear. Again, the key here is understanding that velocity is just the derivative of position. Number 2, what is the speed of the polar bear at time equals 3? Well, remember, the definition of what speed is just the absolute value of the velocity. What that means in this case is I can do the exact same thing I did before, where I go 3 times 1 over 0.2 times 3 to the third times 0.63 squared, where I'm finding the velocity. And when in this case you just get positive 3, the speed is just the absolute value of that number. So if that number were negative, I could just make it positive, and that would tell me what my speed is. It's already positive, so it stays positive, because that just means it's moving in the positive direction. So my speed of the polar bear is 3. Again, units don't matter right now, but it would be meters per second. Now, for the polar bear speeding up or slowing down, what we would have to do, there's lots of different ways we could do it. We could take the derivative again, and we can compare the velocity and the acceleration at time equals 7.8, or you can graph this on your calculator, and the part that we're interested in is the graph that looks like this right here. I believe this is up here. I could be mistaken on this part because that part's unimportant. But over here, we're looking at this graph. Now, all I want to do is I want to see what is happening at time equals 7.8, which is roughly right there on the graph. That's where time equals 7.8. And I can find that by graphing the graph in my calculator, then pressing the trace button, and then typing in 7.8 and pressing enter. So once we do that, then we know, because this is a velocity graph, that two things about it. Number 1, the velocity is above the x-axis, so the velocity is a positive number. The other thing that is true about this graph is that this function is decreasing, which means the acceleration at that point is negative. So those two do not match up, so I can see that it is slowing down. An easier way that we could do that, if we're just looking at the graph, is we could say, all right, this right here is this graph is moving towards the x-axis at time equals 7.8, which also means it is slowing down. So either way, you want to look at that. That is how you tell whether it's speeding up or slowing down, and that way will work just fine. Now, on the average rate of change, remember, average rate of change, and this is something we talked about previously, average rate of change, what we do is we find the slope between 2 points. So my x values, because that's the interval we're looking at, the x values here are from 3 to 7. So I just take those numbers and I plug them into my original function. So I plug them into this 3ln of 0.2 times x to the third. When we do that with 3, we get 5.059, and when we do that with 7, we get 12.685. So now I have my 2 points. I just need to find the slope between those 2 points, and that will give me my average rate of change on this interval. So 7 minus 3 here. And I actually haven't typed that into my calculator yet. Give me just 1 second. So when I type that in here, I get 1.9065. So that is my average rate of change. Now again, that is just the slope between two different points that exist on the original function. So it doesn't have anything to do with the derivative. If I ask for the instantaneous rate of change, that wants to know the derivative at time equals 4. Well, just like earlier, we know what the derivative is. It's 3 times 1 over 0.2 times, I'm going to put 4 into that derivative, multiplied by 0.6 times 4 squared. And when we do that, what we get is you actually get 2.25 when you plug that in to your calculator. Okay? So 1 through 5 I actually thought were much more difficult than the next ones we're going to look at, but that is how we use a function to answer these questions. Now what we're going to be doing is we're going to be given a velocity graph. Okay, now remember, this is a graph of the velocity. We're no longer looking at position, so we have to interpret this differently. So when the particle is moving forward, what is happening is I have a positive velocity. So that happens from right there to about right there. Now that's kind of hard to see, but I would say that that happens from about 6 to about 12.5 is when it's moving forward. The rest of the time, my velocity graph is below the x-axis, so it's moving backwards the rest of the time. So from time equals 2 to time equals 6, it's below the x-axis, and from time equals 12.5 all the way over to time equals 19 is when it's moving backwards, because that is where my velocity graph is below the x-axis. When is the particle moving at a constant speed? That's when it's neither speeding up nor slowing down. So in this case, that's when my velocity graph is flat. So in this case, we would see that that is from 7 to about 12 is what I would say when the particle is moving at a constant speed. Because what we're talking about, again, is this flat line up here. On what time intervals is the acceleration positive? Well, if I have a velocity graph, what I'm looking for is I want to see where the velocity graph is increasing. So I see two different places that my acceleration is going to be positive. That is from from 5, I apologize, to 7. So that interval is too wide. That's what I was thinking. And then also, looks like from 14 to 16, my acceleration is positive as well. And then last but not least, when is the particle speeding up? Remember, when we're looking at a velocity graph, that is any time the graph of the velocity is moving away from the x-axis. So I can say from 2 to 5. Also from 6 to 7. I could also say it's speeding up from 12.5 to 14. And those are the three different places the particle is speeding up. Slowing down is any time my graph is moving towards the x-axis. So we'd have like from 5 to 6, because that's when the graph's moving towards the x-axis. Also from 12 to 12.5, it's slowing down. From 14 to 16, it is slowing down. And from 18 to 19, it's slowing down as well. You'll notice that these flat lines, it's neither speeding up nor slowing down again, because that is when it's moving at a constant speed. When is the particle at rest? Now remember, that's when the velocity is equal to 0. So the first place it's at rest is entirely from 0 to 2. Then again at time equals 6, at time equals 12.5, and then from 19 to 20 as well, because my velocity is equal to 0. That's what it means to be at rest, is when the velocity is equal to 0. Again, hopefully all of those questions made sense on how we got the answers and why the answers are the way they are. If you have any questions about this or any questions from the first review, please let me know so that we can get you ready to take the test.